Okay, our lecture video for 3.2 was on the shorter side, about 15 minutes. So we've got 5 exercises picked out to review how to take derivatives of exponential functions and how that applies to certain problems. They shouldn't take too long, but let's dive in with the first one, which is number 9 from the textbook. In exercises 1 through 25, the directions are to just find the derivative and assume that a and k, if you see them, are constants, although in this example we don't have any of those. So our function is the sum of two things. It's 3 to the x plus 3, 3 to the x over 3 plus 33 over x, 33 over the square root of x. There we go. So the rule that applies here, since it's the sum of two things, is that we can write the derivative dy dx as the derivative of 3 to the x over 3 plus the derivative of 33 over the square root of x. Now, as always with these derivative problems, there are a lot of different arithmetic steps that you could take in order to arrive at the result, a lot of different routes you could take. For example, one route that you could take, although we're not going to do it this way, is to say, well, 3 to the x over 3 is 3 to the x minus 1. And that's true, although we don't exactly know what to do yet in a situation like that. Instead, we're going to write this just as 1/3 times 3 to the x and realize that this is a constant, so it can get pulled out front. That gives us 1/3 times the derivative of 3 to the x, 3 to the x, plus, now in this case, we've got a 33 in the top. That's also a constant multiple. So that's 33 times the derivative of 1 over the square root of x. Now this first part here, this first derivative, that's an exponential function. That's what we're learning in this section. So we know that the derivative of 3 to the x is natural log of 3 times itself, 3 to the x, plus 33 times the derivative of 1 over the square root of x. This is going to be the power rule. So it helps to write 1 over the square root of x in a power. That's x to the negative 1/2. 1/2 because it's a square root, and negative because it's in the denominator. So the derivative is negative 1/2. That's because the power comes down in front as a multiplier, times x to the power minus 1. So negative 1/2 minus 1 is negative 3/2. And this is our answer. Perfectly fine if you want to leave it like this, although we could simplify it a little bit and say natural log of 3 times 3 to the x over 3 minus 33 over 2 times x to the 3/2. I'm not going to be too big of a stickler regarding simplifying, as long as you don't miss something that simplifies a really messy expression into a really simple one. Things like this are not necessary, although it sometimes helps to write it in this nicer format here. Okay, so that's 1 out of 5. Let's move on to the next one. This is another find the derivative. We don't have any of these constants a and k, but we do have e and pi. So this mixes a bunch of symbols up, and part of the point of the question is to try to unravel what's a constant, what's not, where's my variable, and so on. So what we have here, we have e to the pi. Well, those are both numbers. That's like 2.71 to 3.14. No idea what it is off the top of my head, but it's a constant. There's no x involved here. So this is a constant. This pi to the x. Pi is a number. X is the variable. So this is an exponential. It's very important that you can tell apart things like x to the pi versus pi to the x. This is a power function. This is an exponential function. The difference is where the variable is. So if we take the derivative of f of x, the first rule says the derivative of the whole sum can be split up into two derivatives. So it's the derivative of e to the pi plus the derivative of pi to the x. Now, as you do more and more of these, you won't have to write out all of the steps. You'll be very comfortable with doing some of it in your head. But for right now, we're going to write them all out so that you can see exactly what properties we're applying. This first one now, we said e to the pi is just some number, whatever this is. The derivative of a constant, as we saw in 3.1, is just 0. The derivative of a constant is 0. So this is 0 plus Now the derivative of pi to the x, this is an exponential. So it's just like 2 to the x, except instead of 2, we have a different constant. We have pi. So the formula applies as normal. The derivative is the natural log of the base, the natural log of pi, whatever that number is, times the exponential itself, pi to the x. Okay, so that's it for this problem. We had a constant that disappeared, and we have an exponential where we just applied our rule. Moving on to the third problem. The next two problems have this form. The question asks, can it be differentiated with the rules that we've seen so far? If so, take the derivative, and if not, say why not. So at first, this looks like it can't be, because we know how to differentiate things like e to the x, but this has extra things up there in the power. But this time, we're saved by applying a rule of exponents. E to the x plus 5 by our rules of exponents is e to the x times e to the 5. Remember, the general rule is that e to the a plus b, sorry, let me use all constants here, a to the b plus c is a to the b times a to the c. So that's the rule that we're using here. Multiplication on the outside of the same base corresponds to addition up there in the power. So we can write this as e to the x times e to the 5. And now let's try to take the derivative. The trick is that e to the 5 is a constant. It's 2.71 to the 5th power, which is, I don't know, whatever it is, it's a constant. So that means it can get pulled outside of the derivative. So what's left is e to the 5th, on the outside now, times the derivative of e to the x. What's the derivative of e to the x? This is the funny one that we saw in the lecture. The derivative of e to the x is itself. So this is the derivative. Now if we want, we can apply this rule and stick them back together. And see that the derivative of e to the x plus 5 is e to the x plus 5. So e to the x is its own derivative, and I said that was a rare thing, and it is. But it follows from that that this closely related function, e to the x plus 5, is also its own derivative. Okay. Now, moving on to this one, this is number 35. Same instructions. Can it be differentiated? If so, do it. And if not, why not? This one it's an exponential with something more complicated than just the variable in the numerator. In this case, it's not the numerator, the power. In this case, it's x squared, not just like x plus 5. So can any of our rules of exponents save us? Well, let's remember our rules. We just saw a to the b plus c is okay, because we can split it like that. The other rule that we have is if you have a to the b to the power of c, well, let me write that kind of differently. A to the b times c, let's write it like that, is a to the b to the c. So, can this rule help us? Well, the first rule does not apply, because x squared, there's not a nice way that we're going to be able to write that as something plus something. Well, what about this one? What if we think about b and c as both being x? According to that rule, 4 to the x squared, we could write as 4 to the x times x. Nothing interesting there. That's just writing x squared as x times x. And now, according to this rule right here, we could write this as 4 to the x to the x. But this doesn't help us at all. This is still something that we don't know how to take the derivative of, because it's a function inside of another function. And this is what we're going to learn soon in 3.4, I think, which is how to take the derivative of a function inside of a function, something like the x squared inside the exponential. This will be called the chain rule. But since we're not there yet, we don't know how to take the derivative of this. So this one we can't do. This one cannot be differentiated using the techniques that we know so far. Okay, we've got one more. We're going to keep this probably under 12 or 13 minutes, it looks like. This is a word problem. It says, after a storm, a high-pressure system moves into Duluth. The air pressure T hours after noon, let's highlight that, after noon, is given by this function. This is a constant minus a constant times an exponential. And in fact, notice that this is an exponential decay. Find the air pressure and the rate at which it's increasing at 3 p.m. So this function tells us the air pressure. They want us to figure out the air pressure at 3 and the rate at which it's changing. That's the derivative at 3. Now, before I do that, I want to think very vaguely about what this function looks like, which will help us check if our numbers make sense. We know what an exponential decay looks like. Let me pick a light gray here. Exponential decay looks kind of like this. This is not quite that. It's the constant multiple, okay? That's just going to scale things, not a big difference. But then it's a positive number minus that, so that causes a flip. That means that our function is actually going to look something like this. There will be this number, 1050, and since we're minusing this part, that means the difference here follows that gray function. So it's big here, and then smaller, and then approaches. This is not necessary to answer the question, but if you know this, it will help you check that your answer makes sense. So the first question is, what is the air pressure at 3? That's saying at 3, what is the height? So that's simple. We just plug in 3. 3 p.m. Okay, so we have to make sure the units make sense. 3 p.m. And what is t? It's hours after noon. So that's 3. If it was after midnight, it might be something like 15 that we'd have to plug in. But afternoon, so we plug in 3. And of course, we can all do this in our heads, right? Well, no, of course not. You go to the calculator and you plug this in and you get something like 1013.45. So on a quiz or exam, you would just leave this in this form. On homework on Wiley Plus, you'd plug it into a calculator or just plug it into Google or something and get this numerical approximation. Now, what is the rate at which it's changing? The key here is we have to recognize the rate at which it's changing at 3 p.m. That's asking what is p prime of 3. That's key that you recognize that's what it's looking for. So we need to find p prime of t and then plug in 3. We're not going to write out every step here because we're going to practice being able to do some of it in our heads. But what does p look like? It's a constant minus 44 times an exponential. So when you take the derivative, for starters, the derivative of this minus this is the derivative of the first one minus the derivative of the second one by our rule. And the derivative of this is 0 because it's a constant. So we're doing a couple steps in our head now. If that doesn't make sense, that's okay. Just write them out step by step, and after you do some more practice, then you won't have to do that anymore. So number 1, we get this negative sign coming from here. We get the constant multiple of 44 coming from here, and then we have the derivative of 0.94 to the t, which is the natural log of 0.94 times the function itself, 0.94 to the t. And then to find the actual answer, we look for p prime of 3. That's negative 44 times natural log of 0.94 times 0.94 to the 3. And if I plugged it in correctly to my calculator earlier, that should give us something like 2.261. Okay, let's think about what this actually means and does it make sense? Because at first you might say, wait a minute, something seems wrong. This says that at 3 p.m., the air pressure is increasing, and it's increasing by about 2.2. 2.2 what? We've got millibars and hours. So millibars per hour. So at 3 p.m., the air pressure is increasing at a rate of about 2.26 millibars per hour. At first, though, you might see the negative and think, why did I get a positive number? The key is that natural log of E is 1, right? Natural log of 1 is 0, but natural log of x is negative if x is less than 1. The natural log of a number between 0 and 1 is a negative number. So we have a negative sign But this constant here is also negative, and that cancels to give us a positive. And that makes sense because we drew this picture here. This is an increasing function. So it does make sense to get a positive number at 3 because we have a positive slope. Okay, so that was our 5 exercises. It went by pretty quickly between the lecture and the exercises, definitely shorter than a normal 50-minute lecture. So I hope you watched them all the way through. I hope the exercises helped you understand a little bit about taking the derivative of an exponential function. Make sure that you're doing the suggested homework for extra practice, and then I'll see you in our next lecture.